This is our second video lecture over section 4.3. We're going to look at the binomial probability distribution function, the Binompdf function in your calculator. Using Binompdf in your calculator will do exactly what we were doing by hand in the previous video when we were finding binomial probabilities. Let's look at an explanation of the function's inputs and what it does. Binompdf of n, p, x is the probability of exactly x successes in n trials of a binomial probability experiment, where p is the probability of success in any one trial of the experiment. So as advertised, this function finds binomial probabilities. You have to have three inputs for this function: the number of trials, the probability of success in any trial, and the number of successes. Implicit in that is that you know what a success is in the problem, and that's a choice that you get to make. But you have to make a conscious choice of what your success is in order to find the values of p and x. This calculator function will allow us to avoid having to do all those factorials on our own. We'll be able to do all of this quite efficiently by employing the calculator function. It still takes work, though, because you have to identify these three inputs in every problem. To learn how the calculator function works, we're going to redo a couple of examples from the previous video. And then we'll move on to some new examples where we have to come up with the inputs on our own. And we'll even look at a more complicated example that we didn't touch in the previous lesson. The first example from the last lesson was about coin flipping. A coin is flipped 4 times. Find the probability that the coin comes up heads exactly twice. And you can see all of the work that we did for this problem. On the right, you see all of the inputs that we used to the function, and on the left, you see the formula itself and then the work that we did to crank out the answer. We got a final answer of 3/8. We're going to redo this problem using the calculator function. So let me get rid of that work on the left side. And actually, while I'm at it, I'm also going to get rid of that value of q because we don't need it for the calculator function. Let me remind you of the order of the inputs. It says it's Binompdf of n, p, x. N is the number of trials, and we have it listed down here, it's 4, but that comes from the fact that we're flipping the coin 4 times. P is the probability of success in any one trial, and we determined that was 1/2 because when you flip a fair coin, there's a 50% chance that it comes up heads and a 50% chance that it comes up tails, and we had chosen a success to be heads in this problem because that's what we're counting up. And then the last input, x, is the number of successes. X successes. We want the coin to come up heads exactly twice, so there are 2 successes in the problem. So the calculator input we're going to use is Binompdf of 4, 1/2, 2. Now, depending on the operating system that you're using and the settings that you have, there are 2 different ways that this calculator function looks in your calculator. For our first couple of examples, I'm going to do it both ways, and then I'm just going to stick with one of those 2 options for all future examples. Let me pull up my calculator emulator here. To access Binompdf, we want to get to the distributions, and if you look above this variables key, which I'm actually going to call the vars key, but that stands for variables. If you look above the variables key, you'll see this distr in the same color as my second key. distr stands for distribution. We want to use the binomial probability distribution, and so that's where you're going to find this calculator function. So I want you to push second and the variables key, second vars. The option we want in this calculator is choice A, and it's actually going to be faster if I scroll up to find it. If you have an older calculator, a TI-83, it might be choice 0. You want the Binompdf function. You need to be careful because there's also a Binompcdf function, and in the older calculators, that's choice A. In the newer operating system, in the newer calculators, choice A is Binompdf. That's the one we want, binomial probability distribution function. With the cursor on choice A, with the cursor next to Binompdf, I'm going to hit enter. And with the newer operating system, you get this input screen. It tells you exactly what the inputs mean. The first input is the number of trials. Well, that was 4. Then I can hit enter or the down arrow. I'm going to hit enter. P is the probability of success. And our probability of success was 1/2, which you can enter as a fraction, 1/2. You can also enter the decimal equivalent, 0.5. I'm going to enter the fraction because that's the way that we wrote it on the screen. But you could also use the decimal 0.5. Enter to get to the x value. The x value is the number of successes, which is 2. Enter again. And paste is a command that will paste this calculator function to your main screen. So I hit enter, and you'll see it pop up. Your text might not wrap like this. I've set it up so that you can see the text wrap on the screen. Your settings might not allow for that, but you should be able to see the end of the input. Hit enter, and we get 0.375. If you remember when we did it by hand, we got an answer of 3/8. And if we check the decimal equivalent of 3/8, we see that that's 0.375. You get the same answer. The calculator function is much more efficient most of the time. I am going to require that you use the calculator function for our problems, even if you like doing it by hand. The calculator function is going to be a requirement in this class. So I want you to get used to using it. Now I'm going to turn off my stat wizard and redo this for those of you that don't get that input screen. It starts the same way with second and the vars key. I still want option A in this calculator, Binompdf. Hit the enter key. And you'll notice instead of getting that input screen, it just pastes a Binompdf on your main screen and now asks for the input. So you have to know the order of the inputs. And it's n, p, x. Number of trials, probability of success, number of successes. So you start by typing in the value of n. Then you type a comma. The comma key is above the 7 key. Then the probability of success has to be a number between 0 and 1. Doesn't matter whether you type it as a fraction or a decimal, but it has to be between 0 and 1. Comma again. And then the number of successes, which was 2. If you want to close the parentheses, that's above the 9 key. Hit enter, and there's that 0.375 again. So our probability came out to 0.375, which is 37.5%. It's also 3/8 we know from when we did it by hand. My expectation is when you use a procedure that gives you a fraction answer, you'll report your answer as a fraction. Similarly, now that we're using a procedure that gives us a decimal answer, I would expect you to give me a decimal as your response. That seems like the natural thing to do. But you're welcome to turn it into a percent if you'd like. A lot of people feel more comfortable interpreting percents than decimals. In a casual conversation, most people would report probabilities as percents. They would say there's a 37.5% chance of such and such happening. They wouldn't say the probability is 0.375. But us math nerds use those decimals. So it doesn't matter to me which one you use, and it just seems natural to use the decimal since that's what the calculator is going to give you anyway. Let's practice the calculator function again using an example we've already done. The other example we did in the previous lesson was about rolling dice. A die is rolled 3 times. Find the probability of rolling exactly 1/6. And so we came up with the inputs. We said that the number of trials was 3 because we were rolling the die 3 times. The probability of getting a 6 on a 6-sided die is 1/6. We got the probability of Q as well, but we won't need that for the calculator function. And if we want exactly 1/6, then the number of successes is 1. The answer we got was 25/72. Let's see what we get by using the calculator function. So I've taken out all of the work. We're also going to take out the value of Q because we don't need it for the calculator function. We're going to input to the Binompdf function the inputs 3, 1/6, and 1. Again, I'm going to demonstrate this for both operating systems, for both settings. First, we'll do it for the newer operating system. We're going to push second and the vars key, and we want option A. So I'm going to scroll to it. I am going to show you how to select option A without having to scroll to it. I want to scroll the first couple of times because I want to remind those of you with the oldest calculators that you actually want choice 0, not choice A. Just make sure you're picking the one that says Binompdf. And if you're not confident which option that is, then you can just scroll to it. With the cursor on the choice you want, you hit enter. We're going to change these inputs. We're rolling the die 3 times. The probability here was 1/6, and here I do not want you using the decimal because it's not a terminating decimal. The exact value of p is 1/6, so don't use a decimal approximation like 0.17 or 0.166666. Just use the fraction 1/6. The number of successes was 1. We're going to paste that on the main screen. Oh, you may have noticed that time I used the down arrow instead of the enter key. It works the same. Hit enter, and we get this decimal 0.34722222222. Going back to the slide where we did all the work ourselves, our final answer was 25/72. Let's see what that decimal equivalent is. 25/72. It's going to be a non-terminating decimal. Same answer, because it's the same result. Just more efficient to do it with the calculator than it is to do it by hand. When you get a long decimal like this, I want you to give me a few decimal places, but because I'm requiring that you show your work, you don't have to give me all of them. 3 or 4 would really be sufficient. So 0.3472 is a fine answer. Technically this is an approximation, but I'm going to hurt my own eyes and use an equal sign. This is around 34.72%. Now that is an approximation, but I don't expect you to check to see if you can write it as a nice fraction every time. You can just give me the decimal. If you're using a sample space or if you're using a formula that outputs a fraction, well then it makes sense for you to report your answer as a fraction. If you're using the calculator function, which is almost always going to give you an output which is a decimal, then it seems natural to me that you would give me a decimal answer, so that's what I anticipate. Let's rework this for the older operating system without the stat wizard. And this is the method that I'm going to use for the remainder of the examples because it's not as intuitive. It doesn't tell you what the inputs are, so it's a little bit harder to use. That's the one I want to demonstrate more. You still push second vars. You still want the same option, Binompdf, which in this calculator is choice A. But now you have to type the inputs in one at a time separated by commas, and you want to type it exactly the way that we wrote it here. 3, 1/6, 1. 3, commas above the 7. 1/6 is 1 divided by 6. Comma, 1. You actually don't have to close the parentheses on the end. Hit enter, and of course it's the same result. You just have to know the order of the inputs. The calculator doesn't prompt you for the order. Now after seeing these two examples, it's quite possible you fall into one of two camps. You might think that these problems are especially easy because we're running to the calculator, or you might feel especially confused because you're not getting the context because we're just typing in inputs that we had from a previous lesson, and maybe you're not making the connection to how we got them. I want to meet both of those groups in the middle by doing some examples where we don't already have the inputs. That way you can make a connection between the problem and the inputs that we chose, and also hopefully see that while the calculator function does make some parts of this problem easier, we still have a significant amount of thinking to do. There's still some work to be done in these problems. Here's a fresh example. A website reports that around 18% of adults get less than 6 hours of sleep per night. A random sample of 4 adults is selected. Find the probability that exactly 3 get less than 6 hours of sleep. Okay, first things first, let's back all the way up. If we're going to use a binomial approach, then we have to verify that this is a binomial probability experiment. There have to be a fixed number of trials, and each trial has to have 2 categories of outcome. But we have both of those here. We have a fixed number of trials because we're selecting 4 adults, and for each of those trials there are 2 outcomes. Either the person does or does not get less than 6 hours of sleep. There's this third issue of independence, but I've told you if you verify those first 2 conditions, you can assume the independence. Once you've determined the problem is a binomial probability, my advice is to make a list of the inputs, which are n, p, and x. Recall that n is the number of trials, p is the probability of success, and x is the number of successes. We've already identified n. There were 4 trials, there are 4 adults, n is 4. P and X are dependent on which outcome you consider to be a success. Remember, we've got 2 categories of outcome. People who do get less than 6 hours of sleep, and people who do not get less than 6 hours of sleep. You need to choose one of those to be a success, and you can actually do this problem with either choice, but my advice would be to pick whatever the problem is asking you to count up. We're looking at the people who get less than 6 hours of sleep. So to me, a person who gets less than 6 hours of sleep is a success. I don't require that you write your successes out, but you at least need to mentally note which outcome you consider to be a success, because that affects the value of P and the value of X. P, for example, is the probability of a success. So what is the probability that you select a person who gets less than 6 hours of sleep? Well, 18% of all adults get less than 6 hours of sleep per night. And so if you randomly select a person, the probability that they get less than 6 hours of sleep is 18%. For the calculator's purposes, we'll want to enter that as a decimal or a fraction. I would use the decimal 0.18. That's the probability of success because we've declared a success as somebody who gets less than 6 hours of sleep. X also depends on your success because X is the number of successes. We are interested in the probability that exactly 3 of the people we selected get less than 6 hours of sleep. And we've said a success is a person who gets less than 6 hours of sleep. We want 3 of these successes, so X is 3. Both P and X go back to what you've chosen a success to be. And in a lot of examples, like this one, there's a natural choice. But in some examples, you might not go with what I consider to be the natural choice. And I'm telling you that you can still do the problem. You just have to be aware of which outcome you've selected to be a success. Because we want the probability of exactly 3 successes, we can use the Binompdf function. This is Binompdf of 4, 0.18, 3. We're going to put that into the calculator. And this time I'm going to show you how to select choice A without scrolling to it. So if you push second in the vars key, and you know you want option A, if you look carefully above the math key, you'll see a green A, same color as your alpha key. So you can push alpha and the math key, and that will select choice A without having to scroll to it. For those of you with the older TI-83s, you want choice 0, so you can just push the 0 key. That one's pretty straightforward. For those of you that want to select option A, it's the green alpha key and the math key. To play it safe in the rest of the examples in this video, I'm going to scroll to the option. But in future videos, I might use the alpha shortcut. I can see our inputs off to the left. It was 4, 0.18, 3. Close the parentheses. And I get an answer of about 0.01913 if I round to 4 significant digits. 0.01913. The 3 comes from rounding up. Let me put that output back on the screen here. The 8 would round that up. If you accidentally rounded that down, I wouldn't count it wrong because I'm going to require that you show me this input. If you're curious what my expectation is for showing your work, it's this last part right here. That is required. The other stuff I'd like to see, but it's really repetition to show me N, P, and X off to the side and then as your inputs. So I don't think that's necessary. I also think it's a good idea for you to explain to me what a success is, but I don't require it because if you've done the problem right, I can deduce what your success was. What I require that you show me is what calculator function you used and what your inputs are, and I think this is a good way to type that. And then of course I want to know what your answer is. You can leave it as a decimal. For those of you that are more comfortable thinking of them as percents, that's around 1.9%. So if you were to select 4 adults at random, the probability that 3 of them would get less than 6 hours of sleep is only around 1.9%. It's pretty low. So it would be kind of rare to have that happen. Let's look at another example. It says you and your friend play a game where each player should have a 1/3 chance of winning with a 1/3 chance of a tie. So there's a 1/3 chance that you win, there's a 1/3 chance that your friend wins, there's a 1/3 chance of a tie. A good example of this is rock, paper, scissors. If either player employs a completely randomized strategy, then they have a 1/3 chance of winning, a 1/3 chance of losing, and a 1/3 chance of a tie. However, you've lost 10 games in a row. What is the probability that you lose 10 times out of 10 if we assume your friend is not cheating? If your friend is cheating, then there's no reason these probabilities would have to hold. Your friend would probably have a more than 1/3 chance of winning because they're cheating. But we're going to run with the assumption that they're not cheating and find the likelihood that our friend could win 10 games in a row. First off, and this is a little bit sticky, is this binomial? Is this a binomial experiment? You could win, you could lose, you could tie. That sounds like 3 outcomes, and that's not binomial. But what we're going to do is lump winning and tying into a single category that we call not losing. We're looking for the probability of losing 10 times in a row. And so we'll make a success when we lose, which I know sounds backwards, but success isn't about good or bad, it's just about what you're counting up. So a success will be when we lose, and a failure will be when we don't lose. And that's how we're going to turn this into 2 categories. We also have to make sure that there are a fixed number of trials, but it asks for the probability that we lose 10 times out of 10. So we're 10 trials, we're good there. This is binomial. Let's make our list of inputs, N, P, and X. N is the number of trials, which we've already determined to be 10. P is the probability of success. And I claim that we want a success to be when we lose. And I think that's the best choice because that's what we're counting up, the number of times that we lose. Now, what is the probability that we lose? If your friend wins 1/3 of the time, that means that we lose those games. So our probability of losing is 1/3. Now, how many successes do we want? Well, we want to lose 10 times out of 10, so X should be 10. And now we're ready to set this up with the Binompdf function. And the lack of space I have actually gives me occasion to introduce you to an abbreviation I'll be using. Instead of writing out Binompdf, oftentimes I'll just write BPDF. 10, 1/3, 10. BPDF for Binompdf. Now we run to the calculator. Second vars, and I want choice A. Remember, there's a shortcut to grab that using the alpha key. We have 10 trials. Probability of success is 1/3. And we want 10 successes, 10 losses. And that probability is about 1.69, right? No. Probabilities are never, ever bigger than 1. If you look off to the right, you'll notice that this is in scientific notation. You are permitted to give your answer in scientific notation, but I'm going to move the decimal to demonstrate how small this probability is. I would first get 4 zeros after the decimal point, and then the 169. Converting this to a percent, that's about 0.00169%. If you're not sure how small that probability is, that's less than 2 out of every 100,000 times. This would be an extremely rare event. It just shouldn't happen. So what's the most likely explanation? One explanation is that you've run into a situation that would happen less than 1 out of every 50,000 times. The other explanation is that your friend is cheating, that those probabilities aren't right. You should have a 1/3 chance of winning, but if you had a 1/3 chance of winning, this event probably wouldn't happen. Is it possible? Yes, but it's very, very unlikely, and the more likely scenario is that these probabilities are wrong. And this is one of the best things you can do with probabilities. I mean, come on, you can use math to call somebody a liar, right? That's awesome. I want to reiterate that this doesn't guarantee that your friend is cheating. It is possible that you've lost 10 games in a row, but it's just such a rare event that it would be hard to believe that your friend was playing fairly. Let's move on to the next example, which honestly I'm really just using to set up the example after that. It says about 10% of all people are left-handed. Find the probability that in a randomly selected group of 5 people, none of them are left-handed. Is this binomial? Yes. We have a fixed number of trials. We're going to select 5 people and ask them the same question. And are there 2 outcomes to each trial? Yes. Because each person is either left-handed or not left-handed. And that's what gives us our 2 categories. We're going to identify N, P, and X. N is the number of trials, which we've already said was 5.
P and X are dependent on which outcome is a success. We're given the percentage of people who are left-handed, and we're being asked about the number who are left-handed, and so I would make a success a person who's left-handed. If we make a success a left-handed person, and 10% of all people are left-handed, then the probability of selecting a lefty is 10%, which is 0.1. We've been asked to find the probability that none of the people in our group are left-handed, so we actually want 0 successes. And I think the fact that it says none of them are left-handed makes some people think that a success should be right-handed people. And if that's the way you see it, I want you to do it that way. It will work. You just have to adjust your values of P and X. They won't be 0.1 and 0. You'll need 2 different numbers. This is Binompdf 5, 0.1, 0. But before we put this into the calculator, let's think about whether or not this would be a rare event. 10% of people are left-handed, so in a group of 5 people, it would not be weird to have no lefties. Let's throw it in the calculator and see what we get. Second bars, I want choice A. Use the shortcut if you want to. 5, 0.1, 0. And we get around 59%. It's 0.59049. So as predicted, this would be a fairly common event. It would happen about 60% of the time. Okay, now here's a follow-up question that's related. About 10% of all people are left-handed. Find the probability that in a randomly selected group of 5 people, at least one is left-handed. Let's approach this like it's a new problem, forgetting that we mentioned that this is related to the previous problem. So this is binomial because we have a fixed number of trials, and in each trial, a person is either a lefty or they're not. We have 5 trials. We're going to make a success a lefty because that's what we're counting up. The probability of success is 10%. And this time we have multiple cases. At least one means one or more. And the Binompdf calculator function isn't set up to take multiple inputs. We would have to do each of these cases independently. So we could type in the Binompdf inputs for all 5 of them like this. You can see I've got all 5 cases typed out, Binompdf 5, 0.1, 1, all the way up to 5, 0.1, 5. And we get an answer that's around 41%. But now let's stop ignoring the fact that I mentioned that this is related to the previous problem and see if we can recreate that answer without all 5 of those inputs. There's got to be a slicker way. The previous example found the probability that none of them were left-handed, and now we want the probability that at least one is left-handed. Those are complementary events. The complement of at least one is none. This event is the complement to the previous event, so we just want to subtract. It's just 1 minus the previous probability. So rather than doing all of that work, we can just find the probability of 0 successes and then subtract from 1. Well, we found the probability of 0 successes in the previous example. So it would just be 1 minus that probability. 1 minus 0.59049, which would be 0.40951. Let's see what we got when we did it with the calculator. 0.40951, same answer. But we can avoid doing all of the individual cases by just recognizing that it's the complement of an easier case. This is around 41%. Again, that's 100% minus the 59% that we got in the previous example. We're going to try to use this complement idea to shorten up some of the problems that we do. We don't have nearly as much work. Let me demonstrate that again, but without the setup of doing 2 examples back to back. A study shows that 81% of American adults own smartphones. Find the probability that in a random group of 6 American adults, at least one has a smartphone. All right, so you're out somewhere. Your phone dies. There are 6 people around. What's the probability that at least one of them is going to have a phone that you could borrow? Let's see. Is this binomial? Yes, we have a fixed number of trials. We're going to ask 6 people. And in each case, they either own a smartphone or they don't own a smartphone. N is 6. P and X are dependent on which outcome you consider to be a success. I think the obvious thing to do is to make a success somebody who owns a smartphone. To me, that's obvious because we're counting up the people who have smartphones and we're given the probability that somebody owns a smartphone. That probability is 0.81. Notice that we want the probability that at least one has a smartphone. So X isn't just 1. We want to consider all cases bigger than 1. All the way up to 6. We don't go past 6 because there were only 6 trials. You can't have more successes than trials. I guess one way to do this problem would be to do the Binompdf inputs for all 6 of these X values and then add them all together. But we saw in the last example that it was easier to use the complement, and that's true here. If it's not the case that at least one person has a smartphone, then none of those people have a smartphone. So the complementary event is the case of 0 successes, 0 people with a smartphone. What's so great about that? It's only a single case. This is what Binompdf is built to do. I can find that probability with Binompdf of 6, 0.81, 0. But that's not the probability that we want. That's the probability that none of them have a smartphone. We want the probability of the opposite event. So how do we get the probability that we want? We subtract from 1. We do 1 minus that. I'm going to do this all in one line on the calculator screen. You could do instead what we did last time, which is to calculate the Binompdf function first and then subtract that result from 1. Doesn't matter, you'll get the same answer. So what I'm going to do is type the 1 minus first, and since it's subtraction, you want to use the big subtraction key, not the negation key. So 1 minus, then I'm going to hit second vars. I'm going to scroll to Binompdf, it's choice A in this calculator, and you'll notice that it just appends that right after the 1 minus. So I'll do this all in one line. N was 6, P was 0.81, and we want 0 successes in our complement. Then we're going to subtract that from 1 to get the probability that we want. And we see that it's around 0.9995. I'm going to stop there. I'm not going to do just the 9s, but it's around 0.99995. That's 99.995%. It's almost guaranteed that in a random group of 6 American adults, at least one of them will have a smartphone. I strongly encourage you to look up more examples. Please don't hesitate to ask me questions about those examples or these examples, because while the calculator does make this easier, it does not make it easy. There's still a lot of thinking that goes into this. Let me know how I can help you understand.